Thank you very much for a very kind introduction. So I'm very happy that I have opportunity to present here some results and knowledge which we have accomplished also in our Thundertron laboratory in Nuclear Physics Institute. So I would like to show you the plethora of possibilities, how the ion beams can be used for modification and synthesization of surfaces and materials with specifically sensing properties for photocatalytic properties and let's say also sensing of biomolecules, for example. So here you can see the outline of my talk. So firstly, I would like to introduce you or say something about motivation, why my main examples are based on graphene-based materials, polymers, and zinc oxide nanostructures, how the ion beam modification and implantation can be employed. Then I will speak a bit about experimental things, because we have plethora possibilities, how to use the ions, how to change the parameters, either use broad beams or focused beam, high energy beam, low energy beam, or single ion irradiation, or ion beam lithography. Mainly, I am focused on the, let's say, medium and high energy ion beams, which are typically produced by medium power implanters and Thundertron accelerators. And then I would like to show you results, how the material can be modified and what very extraordinary and interesting properties we have been achieved. So here in motivation, you can see the first kind of material. So graphene now really is very, very popular and topical. And so just remind you that the graphene is material with typical honeycomb structure. And this graphene has remarkable high carrier mobility, extraordinary surface area, which really is great, especially for the sensing applications. And the same way, precursor from which graphene can be created is non-conductive material, graphene oxide, where the plane is decorated with different epoxide and hydroxyl groups. And ion beams can be very, very useful for the modification, reduction of graphene oxide, the extent of reduction, changing of electronic structure of such things, of such surfaces. So here you can see also the small device from graphene. This is sensor of humidity. As the molecules of water are absorbed inside several monolayers of graphene, then the resistivity is increased. So how the humidity is increased, so also the resistivity is increased. So it means that we here see the cycle of as it is absorption and absorption of the water. We can see the cycle of this sensor. This is one very nice example, and has to be said that these materials are very cost effectively produced and can be also recycled. The same way, also polymer can be decomposed, recycled, and reused again. And if we will be able to create flexible electronics in polymers, in graphene oxide, with ion beams also, so then we will have very small devices, very effective devices, which finally can be recyclable. So depending how you choose your parameters of your surface, your material, and the way how you would like to modify, then you can use it for different kind of molecules, also chemical molecules, enzymes, and so on. You can also choose what device you would like to construct, and then you can choose the signal which you will detect, and you will have different kinds of devices which are very which can be used for sensing. So here you can see, for example, graphene structure. electronic band structure and how the graphene looks like. And here you see that we have several possibilities how to modify the surface. And one is particle irradiation, because particles is very, let's say, on nanometer scale, very small probe and very small modification tool. So what we can do, for example, vacancies, we can do topological defects, which can introduce stress into the graphene. So it means that we are changing this electronic structure, and we can modify, we can open the band gap in the graphene, for example, in such a sense. Yeah, because graphene has no band gap, but we can change these properties. Additionally, we can also add heteroatoms. So depends what heteroatoms by ion implantation we introduce into the structure and how we implant them. It means where they will be sitting and what will be the symmetry of the system. And on this symmetry, again, depends the very important feature, and this means that if I implant, for example, metals like a copper or cobalt, so then depending how the cobalt is connected into the graphene structure, and this is the site for absorption of very harmful gases like CO2, like methane, like sulfur, oxygen dioxide, and so on. So again, we can use here ion irradiation. So here is also example how the ion irradiation generally is modifying carbon-based materials. So here we have example of polymers. So in case of polymers, we know that we have several monomers which are connected in between, and it depends on the complexity of monomer. Some polymers are undergoing rather cross-linking in case of more complex monomer, and some of, let's say, simpler monomers are undergoing scission. But also there are free radicals created, and typically volatile compounds escape during the ion irradiation. So typically we have to take into account radiolysis. It means that decomposing or escaping of volatile compounds under the ion beam, or also thermolysis, because polymers are not good heat. Let's say the heat is not transferred well in polymers, and this is how the polymers are modified. But here is a very nice recent example of reduced graphene oxide, where the ion beam of carbon, this is so-called self-implantation, that we are using carbon or oxygen ions if we are irradiating materials which consisted from carbon or carbon oxygen and so on. And under this irradiation with 40 kV energy, these authors achieved nanoporous, in fact, nanoporous materials, which is great because it's now highly needed are various separation membranes. And these separation membranes are important for recycling of lithium and rare earths, for example, lithium from batteries and so on. So again, here the graphene oxide is important, and also is important as a covering of electrodes in lithium batteries, and we can enhance the surface properties of such graphene layer, for example, with ion beams. Other example, as I mentioned in advance, that I would like to talk about it, it's a zinc oxide. Zinc oxide in a nanostructure has plethora of possibilities: nanowires, nanoflowers, nanopillars. There are really, this is material with plethora of nanostructure which can be created. And here is again, and is biocompatible. And also there are recycling method for nanostructures or nano zinc oxide materials. So this is example of glucose sensor. So we have zinc oxide nanopillar. Zinc oxide is semiconductor. So if we irradiated zinc oxide with UV lights. So then we have creation of electrons and holes. And if some harmful molecules absorb on the surface, so then due to the reduction and oxidation processes can be decomposed. So which is great. So it means we can degrade harmful biological molecule or chemical molecule. And these nanostructures have very high effective surface. So it means are very suitable for such kind of applications. So it means that we have very small sensor. We need very small amount of analyte, and under the UV light, the glucose is decomposed, and we can analyze, or we can sense the glucose, for example. So we can enrich it also with nanoparticles, silver and gold, and enhance the electron transfer and enhance the reduction oxidation processes. You can also inhibit the harmful bacteria, for example. So this was reason why we were interested also in this kind of materials. So in general, in such kind of materials, I mentioned what is happening in polymers and in graphene, that we are inducing defects. The same we are doing in, let's say, crystalline or polycrystalline materials. After the ion implantation, we introduced the ions into the materials, and we are, of course, creating the defects. Important property of ion implantation is that if you have monoenergetic ions, you can very well predict what will be the depth and what will be the thickness of the enriched layer, which is very important for you to know it in advance. But we can use, as I mentioned it, for example, implantation of gold and silver to create nanoparticles. Okay, but you can also modify the electronic structure, because via ion irradiation, you are creating, as you see, you can create the interstitials, because they are taking place ionizing processes, releasing electrons as the radiation of ions is going through, and also ballistic processes. It means that the target atoms are knocked from the origin position. And then you create interstitials of oxygen, for example, or vacancies of oxygen and vacancies of zinc in zinc oxide. It means that you create new levels in band gap. And it means that you extend or shift the absorption of the light, which can be useful for your application. So now here you can see the example how we are realizing this simulation. Typically, STRIM program is very often used because it's a powerful tool and can give us more information. So first of all, we have to take into account that we have nuclear stopping and electronic stopping. It means now depends what energy, what mass of ion we will choose. And then it means that we employed either more electronic stopping or ballistic processes. And on this depends how we will modify our structure. So here you can see how the electronic stopping and nuclear stopping depends on energy. So as the ion is heavier, like oxygen and carbon, so you see that electronic stopping is increasing, but at energy is about 1 MeV. And the nuclear stopping collision, let's say, processes are strongly depleted. On the other hand, at low energies, opposite, and nuclear stopping is taking place. So from the simulation, from this point of view, this is very simple, shown how the defects are created. Typically, we are creating point defects, so-called Frankel pairs, where vacancy and self-interstitial appeared. But of course, these defects can accumulate and can migrate and so on during the implantation in a crystalline materials. So here is one example of ion implantation. So this is the creation of silver nanoparticles with quite low energy to create nanoparticles close to the surface. So upon the SRIM simulations, these particles will be mainly concentrated in the depth about 60 nanometers under the surface. And so here you can see the main principle of ion implantation. So you are typically using broad beams, and you have to choose your energy to know where will be your enriched layer, and to choose the fluence, because as you increase the fluence, so you can expect modification, or let's say spread of the implanted atoms. But with the increasing fluence, you can expect precipitation and coalescence of nanoparticles, so you can create supersaturated layer. In our case, the dose was high enough to create quite small silver nanoparticles. And here you can with big advantage to use also Rutherford backscattering spectrometry, as you see here. So this is the glass with gold nanoparticles, where you see directly the signal in RBS, and you can check very easily whether your depth profile in RBS is in accordance with your theoretical prediction. And here in transmission electron microscopy, you see that you really created nanoparticles. So as I mentioned it before, the simulation by SRIM is very complex, and you can see quite complex detailed simulation. So then you know how will look like my distribution of ions with the chosen energy. This is gold, 400 keV in zinc oxide. So I see that the mean, the projected range and the mean value will be about 60 nanometers, that the standard deviation is about, I don't know, 20 nanometers. I can also follow what will be the zinc vacancies depth profile, oxygen vacancies depth profile, what will be also the deposition of energy via ionization and via collisions. So all these things are important before we start to irradiate the sample and realize the implantation. So now we are moving to experimental part. Here is important, of course, it's done in a vacuum chamber. Your beam must be monochromatic, I mean the monoenergetic beam. And what is important that ion implantation means that we are using broad, very broad beams. And the reason is that we need as homogeneously as possible irradiate whole surface to modify very homogeneously the surface. For this purpose, we typically can use, for example, electrostatic scanning system, which is scanning the beam such a way over your sample. And then you have to ensure several things. You have to follow what is the ion current, because you need to control the ion current to be the same during the implantation. You have, of course, to know what will be your final fluence. You need to know what will be your time for implantation. And in some special cases, for example, in case of polymers, you need extensive cooling to avoid as much as possible thermal problems or dissipation of heat. And on the other hand, you can also use increased temperature in case you would in other kinds of materials, semiconductors, support self-healing or self-annealing effects. You need also Faraday cups here, which are checking your beam all the time during the implantation. So this is the special software with all parameters which you put inside the system when you start your experiment. So here you can see other kind of beam. Now the beam is not broad, but opposite. We are squeezing the beam with the triplet of magnetic lenses to very small area. This is called microbeam, and this microbeam can be used for several purposes. And one purpose is to create, you can see here the real creation of, in a real-time creation of microstructure in Pyrex. And again, in our case, we can software where you in effect create before device or structure which you would like to write inside your material. So in this case, you can see that we are writing quite simple structure. And for this purpose, you need, again, very good control of focusing of the beam, control of the fluence, which is finally delivered on the surface. And you can create really quite complex devices and samples, so, or hierarchical systems. So this is other application of the beam, because if we create the microstructures, or as I will show you later on, we create micro membranes with micro pores, so we also would like to investigate them. And there can be helpful, very helpful, again, ion beams. So this focused ion beam can be used not only for ion lithography, modification and creation of microstructure with high current, as I mentioned it before, but it can be also used for, after the deposition, for the checking what is the elemental maps, what are the elemental maps in such a structure. So this is not structure of microstructure. This is porous dimethyl siloxane, which is a special polymer with silicon. And this is mixed with graphene particles. And you see that these porous materials, again, are very prospective, for example, for sensing. And we can use either very low current regime with femtoamps for scanning transmission ion microscopy. So if I have very, very thin sample, porous sample, I just let the protons go through this sample, and we can see in the surface, in the depth, as here is the depth scale, what is the development of the pores, how the porosity looks like inside the whole sample. And simultaneously, if we increased the current, so we can scan with the beam over the area, and we can uptake the PIXI X-ray spectra and RBS spectra, and from this we can see the elemental maps. So in this case, we see the silicon map, and these are open pores, and here around is silicon, because this is silicon is part of this PDMS. And here again, you see silicon around. But when we analyze RBS spectrum, so we see that this is pure PDMS. Again, the pores are the same, and carbon is around, and these pores are free. So if we mix it with graphene, so these pores, which were empty concerning the silicon, start to be filled by carbon. It means that graphene is filled with the pores. So you have really very versatile tool, which can not only deposit, but also can then analyze your sample and your structures, which you have been created. So now we are moving to applications. So again, I have two applications: zinc oxide nanostructures and graphene-based or graphene oxide-based materials. We are going back to the zinc oxide. We thought about nanopillars, which would be interesting to enrich with nanoparticles. Okay, so our intention was to implant them. We knew that our nanopillars are about 420 nanometers high, are not so perfectly narrow, but okay. And we decided to choose the energy such a way that we would create some small nanoparticles in the upper part of these nanostructures. For this reason, as I mentioned before, we need theoretical simulation. So first of all, we provided theoretical simulation for gold and silver, what energy I will need, and what will be the theoretical distribution of gold and silver in the depth. And what you see, our intention was to have it in the same depth. It means to enable possible bimetallic particle creation. So we had samples implanted only with gold and then with combination of gold and silver, when we kept silver fluence the same and increased the fluence of gold. And again, after the implantation, and we would employ again RBS, because RBS gives us very nice spectrum where we see we are using helium ions with 5 MeV, and we saw gold signal, silver signal, and zinc signal. So from this, we can, let's say, quantitatively, or let's say qualitatively, get the depth profiles. But we have to be, of course, careful, because we are doing depth profiles for very porous materials. So anyway, it's information how much of gold and silver we introduced and what is the distribution. Here we see the prediction, which is pretty narrow. In effect, finally, this implant is much more spread over the zinc oxide nanorods. This is the surface of the nanorod, and this is, let's say, the end of the nanorods. But we have to say that, as I mentioned before, this is porous material, so this analysis is not so precise in this case. But what we saw clearly is that we are losing zinc after the implantation. So it means that the thickness of the layer of zinc is squeezing with the increasing ion implantation fluence, which would be expected. So now we would like to know more about the internal structure, and we employed XRD. And in this case, we found out in the XRD that what is happening, that this material is polycrystalline. This is polycrystalline material, and we can identify in this column and this nanopillar so-called basal domains and vertical domains. And interesting is that these vertical domains, it means domains in the direction when the ions are coming, is squeezing very, very significantly in comparison with these basal domains, which there is also decreasing of the sizes, but not so significant. So here we see that with increasing fluence, we saw that let's say, the internal stress and radiation, let's say, damage is not so critical if we are using combination gold and silver, because silver is lighter and is not so much deteriorating the structure of nanopillars. And here we can see then how they look like. So this is pristine sample. As we increased the ion fluence, we see really also in scanning electron microscopy that there is modification, there is narrowing of these upper parts, and in the bottom parts you can see the deterioration of these nanopillars, which is very well seen also here if we are measuring refractive index. So the refractive index, of course, in case of zinc oxide, this is the bottom and this is upper part of nanopillar, is not the same, because there are spaces with the air. But if we irradiate it, so we see that we decrease significantly in the upper part of this pillar, we decreased the refractive index, which means that this is in good agreement with scanning electron microscopy, where we see the narrowing of the upper parts. But what is important, whether we were successful with our nanoparticles, it seems that yes, that there are nanoparticles, because if we compare extinction coefficient, it means, in fact, absorption of light for different wavelengths. So we saw that with increasing fluence, we really saw increasing absorption peak connected with the gold. So, okay, so this is good for us. And what is the next? The next is to use other optical methods like diffusion reflection spectrometry, where we would like to check whether we were successful with the nanoparticles also from optical point of view. In case of gold, we again see absorption peak, or let's say reflection peak, is increasing with the diffluence. And if we have combination of gold and silver, we see very interesting thing that in case for low fluences of gold, we see two maxima, one in region of surface plasmon resonance for silver, one for surface plasmon resonance for gold. But at the highest fluence, we see only one, something in between. So it might be that really some combination of or bimetallic particles can be created. So this is important. Now, last, we check the properties for photocatalysis. So zinc oxide has really great photocatalytic properties. And we can see that pristine sample is perfect. So we check it with rhodamine, which is organic dye. So you have solution of this organic dye, you put inside your pristine and modified nanopillars, and then you switch on the UV light, and you see decomposition of this organic dye. And here we see that the rate in case of nanopillars modified with nanoparticles is not so high as pristine. But the reason also is, as we saw in our optical spectra, that we extend significantly the wavelengths. So this is our next work. We have to check it for much more extended spectrum of light, which can be used not only UV light, of course, but also we should extend it to longer wavelengths. And anyway, again, it seems that silver and gold combination is quite good. So this was an example of modification of zinc oxide nanorods, where was shown how the ion beams can be used for modification for zinc oxide, creation of nanoparticles, and also analyzing them after that. And we change their optical properties and create nanoparticles there. Now we are moving to the next materials, graphene-based materials. So I remind you that graphene oxide is such a special structure with this decorated with this oxygen-based groups. And here I would like to say that first we have to check, we would like to do microstructures in graphene oxide. We have to reduce locally graphene oxide with a microbeam. But firstly, we need to know how it will react on our ion beam treatment. In this case, we use 5 MeV carbon ions, and we irradiate the graphene oxide. You see that the penetration depth is quite high, about several microns. So this is the projected range. You see what are the mainly electronic stopping is taking place in this case. Then we use RBS to check how we change after the irradiation the composition. And you see that carbon is increased and hydrogen is released, which is expected. But important is that we really created reduced graphene oxide, because we see that functional groups which were here under the beam just disappearing and are escaped, which is our goal. And with Raman spectroscopy, we saw increasing of so very well-known G peak. It means that probably under the beam, as these groups are released, in fact, defects in the structures, the graphene domains can grow. So after that, it means not only graphene oxide was tested, but also polymers. After that, we decided to test with the forecast beam, and our intention was create a micro-capacitor. Micro-capacitor device. So here you can see in graphene oxide quite good quality of the microstructure, very bad quality in PMMA polymer, which is strongly degraded and decomposed under the beam, and quite good quality also in polyimides. And What next? We have to prepare our device. So we have such gold contacts, and with our microbeam, 5 MeV carbon, we create this microcapacitor. We can create different kind of structures. And here we see what is the aspect ratio. It means how it looks like in the irradiated and non-irradiated part. Irradiated part became conductive, the graphene domain appears, and non-irradiated part infects are not influence, are not non-conductive. So this is, in fact, the size is 10 micrometers are irradiated length, and species in between are 20 micrometers. So then we tested it and we found out that really in graphene oxide it works well, because when we measure voltage frequency dependence, we found out in comparison with big, let's say, standard capacitor, that the behavior is in graphene oxide, this device is functional like a capacitor. And if we use the humidity, we see that the scaling of the response of this voltage and resistivity is really changing with the humidity. As the humidity increases, so again increases also in fact resistivity of this device. So it is functional as a sensor of humidity, but can be used also for other kinds of gases. And what is the next? So we would like to do these microstructures in graphene, but we saw that anyway, in the graphene, not so perfect. There are some edges, which there are platelets. So we would like maybe improve our microstructure and use a higher ion fluences for the microstructuring. In such case, we used graphene oxide covered with PDMS, and we found out that if we have pure graphene oxide, and if we use covering with PDMS, which is permeable for the volatile compounds, it means that the reduction of this graphene oxide in escaping of oxygen-rich groups is the same in these both cases, but here the PDMS is avoiding the destruction of the microstructure in case we are using very high fluences. And the same way, also by this way, ion beam, with focused ion beams, again, we use carbon 5 MeV. So we were able to produce functional devices, microcapacitors. So last but not least, we can create with the beam, with this focus beam, because there are possibility how to move the beam. In our case, we use now here oxygen, 12 MeV, which were produced from Thundertron accelerator for the micromembrane creation in PET. In this case, we use such a procedure that we have, we were not broadly steering the beam, but we in fact directed the beam to this position, this position, this position, this position, very small amount of ions to ensure that to each position statistically will be impinges at most with 3 ions, and the lowest case 1 ions, 1, 2, or 3 ions. If we use it, so we received such a regular pattern of let's say 3 ion hits in each point. After that, we have several possibilities: irradiated with UV light and use chemical etching. I have to say that before, this was direct green method, I mean microstructuring of microcapacitor without any chemicals, without any agents. Now this is the first time when we are using any agents, I mean etching, to create the pores. And in such a case, it depends whether we use UV light and etching procedure or we are not using UV light. And what is again very nice, that we can, our ion beams used with scanning transmission ion microscopy to test what is the morphology. It means how look our pores. So as the protons are penetrating the sample, so if they are going, this is here this example, if they are going via pore, so inside, so here you see in high energy part such a peak. This is small peak because the area is small, and there is a main peak where the energy is lower because the ions are penetrating the area where there is not empty space. So in such case, from this spectra, we can simulate and look how the pores look like. So if we are using UV light and etching, so then we have very broad and conical pores, but this was not our intention, because biologists would like to have such kind of pores. And this can be achieved without UV light. And because these pores can be used for trapping the cells and to inhibit the moving through the pores, just trapping and feeding them in the micrometer pores. So this would be other possibility application, let's say bioapplication for sorting the cells. So the micropores are functionally, cells can be trapped. Of course, if the pore is too large, so then the cells can go through. So, but it means that we hope that it could be robust, more robust technology to create pores of different shapes upon the application. So this is very interesting. And last example is example which is connected with the copper implantation. Again, we are using copper ions, and we would like to spread them in different materials, such as graphene oxide and different polymers, but in a very near surface layer. So for this purpose, we really need let's say low energy ions, in this case 20 keV. And we also can use very low fluences just to spread the copper, and also quite high fluences to check what will be the difference. And you can see here the simulations again, which must be done before. And you can see again, Rutherford backscattering spectrometry is employed, and we check what is the chemical composition after the irradiation, where we see very good agreement with the profile of oxygen, depletion of oxygen. And here's the profile of copper. This is experimental, and this is simulation. So why we are doing this? I mentioned it also before, that there theoretically exist works which predict how you could place, for example, the copper or cobalt into the graphene. What should be the symmetry to be ideal for sensing different molecules? Each molecule, depending on symmetry of these sites which are created with copper in these vacancies, depends whether they will have rather absorb nitrogen dioxide, sulfur dioxide, methane, water, or whatever. In our case, the copper was predicted to be mainly very effective for methane and humidity. It means water molecules. So if we check it, we really saw that this is XPS, this is analysis of surface chemistry, where we really saw that after the implantation, there is reduction. So oxygen species, which was expected. But from our point of view, we would like to see if it would work like a sensor. So it means that we measured sheet resistivity with changing humidity after the copper implantation. So here we saw that graphene oxide is for this lowest fluence seems to be good, can be scaled with humidity, but not fully, not in full range on humidity. Surprisingly, polyimide, there's a sort of sort of possibility to scale the resistivity with humidity, but again, for the lowest fluence, it means that the copper is distributed, dissipated in the surface, and we don't need to use very high ion fluence, which finally, as is seen, can be detrimental. But more prospective are these, let's say, very, very low fluences. And then we tested also photocatalytic properties. So, and here we can see that if we tested photocatalysis, so really in case of polyimide, if we compare the pristine samples, and in graphene oxide, we see, especially in polyimide, strong enhancement of photocatalytic activity. Again, this photocatalytic activity is typically measured by this biological, or let's say organic dyes, which are in solution. And when we put the active surface into this solution, we are following absorption spectra from this solution to following how the organic dyes is decomposed in time. So in our case, it seems to be very prospective to use low fluences and to use polyimide and graphene oxide. So in this case, and this is my final summary, ion modification and lithography in polymers and graphene oxide shows us that this is great tool how we can modified graphene oxide, reduced graphene oxide, how we can use microlithography with the MEV ions for rapid green method for fabrication of analog of electronic micro devices, such micro-capacitor, which is small energy storage, flexible small energy storage, and also can work as a sensor. And also this microbeam lithography was effectively used for direct preparation of sensor, as I told before. And we tested also oxygen ions and used them for preparation of various shape of micropores. It means that we tested what parameters, what fluences can be used and what afterwards procedures can be applied to achieve the shapes which are most appropriate for applications such as cell sorting. And this, in this case, we were able to prepare different shapes of pores. And last but not least, we tested the copper ion modification or implantation of graphene oxide and polymers, where we were able to disperse the copper and prepare the surfaces which have extraordinary photocatalytic properties and ability to decompose organic dyes, which was theoretically predicted recently, and we have been able also to see it in reality. So this is end of my webinar. So I tried to show you how ion beams are really very useful tool. You can use them in many regimes. Just remind you, broad beam ion implantation, high fluences, nanoparticle creation, low fluences, single ion irradiation, pore creation, and focused beam usage for ion beam lithography with micrometer resolution. So you have really many possibilities depending on your application. And I suppose that micro devices, micro sensors, and low, let's say, efficient possibility to create polymers and graphene oxide is also a good way how to directly create the surfaces which we would like to have and are functional. So thank you very much for your attention.